So have you seen the adenosine aptamer? Is a single-stranded DNA which is folded on itself and which forms a pocket where two adenosine molecules can fit. This is the general structure of this pocket. So based on the original aptamer sequence, we designed two different structures. So this structure here is made of a long domain here containing 8 base pairs that can match to each other and then form a double-stranded helix that will somehow like lock the structure. And another structure, which is shown here, that contains a much shorter hybridizing domain, shown here with 1 base pairs, 2 base pairs, 3, and 4 base pairs. Okay. So based on these two different structures, we designed different DNA sequences by splitting or cutting this long chain into 2 chains. Okay. So this long chain here is named split aptamer or cut aptamer. And this chain here is named aptamer 8. As you can see here on the other structure, here we do have the same common sequence, split aptamer or cut aptamer, and here a shorter strand that contains only the 4 matching bases, and this sequence here will be named aptamer 4. So we get 3 different DNA strands. One is split aptamer, which is this one. The other one is a split aptamer 8, namely this one. And the third one is split aptamer 4, it's this one. So as you understood, we made some engineering on the original sequence to split somehow the aptamer to get different domains that can reassemble together to form the full and functional DNA aptamer. For each of the sequence, we functionalize the end of the strand with a gold nanoparticles. So you've seen the gold nanoparticle synthesis, and you may know that gold surfaces are reacting with thiol compounds. So thiol compounds are organic molecules containing an SH functionality made of sulfur and hydrogen. These functionalities are quickly reacting with any gold surfaces. So this way, we can graft actually a large number of different DNA strands all the way around the surface of the gold nanoparticle. Then we are ready to assay the adenosine. So for that, we first prepare a sample containing the cut aptamer sequence mixed with the aptamer adenine 4, and then we can add adenosine. Here you have the full formula of adenosine, and play with the concentration, for instance, of adenosine. We can increase the concentration of adenosine and see what will be the minimum concentration to get a sensitive detection of this target. By doing so, we can form this structure here. So you can see that thanks to the presence of adenosine, the full system will reassemble, okay? And then we can get aggregation of this nanoparticle with this one, with other nanoparticles, because don't forget that you get oligonucleotides all the way through the surface of the gold nanoparticle. Then, if there is binding here, you get a full aggregation of all the nanoparticles present in the sample. So here you can see the small pellets made of aggregated gold nanoparticles. If we incubate the similar DNA strands conjugated to the gold nanoparticles with uridine, which is another molecule whose structure is close to adenosine, but which do not fit into the pocket made of both strands here, then we cannot have the binding of the uridine with these DNA strands. Okay, so it means that you cannot form this kind of aggregates. Then you keep the colloidal suspension and keep the red color, which is very characteristic to the gold nanoparticles in solution. Then we can run the control, because if you are doing a biosensor, don't forget, this is very, very important to always have a negative control. You have a negative control, for instance, on the pregnancy test. I'm sure you know that there is a specific band which is very important for the readout and for the conclusions you may draw from the pregnancy test. So if you can, don't forget to run the control. Here, the control we can run is the one which is made of the 8 base pairs, because this sequence here, as you understood, is matching with this one. And because it's quite long, 8 base pairs long, it will be very stable and will form and hybridize together, even though there's no adenosine in the solution. So this control here will help in making sure that you properly functionalize the gold nanoparticles on the aptamer DNA strands. So this is what you can see here. You will form the hybridization of both strands, even though there's no adenosine in the sample. And then you get the aggregate, which is induced by the formation of this double-stranded helix. So here is the series of different samples you will prepare in this assay. So as I said, you will play with the concentration of adenosine by increasing this concentration from 0 up to 0.1 millimolar, 1 millimolar, 2 millimolar, up to 5 millimolars of adenosine. Then you can have the control for the specificity by incubating 5 millimolar of uridine. And then you can run the control between the aptamer 8 and the cut aptamer in absence of any adenosine. Here in this table, you have the details of the different volumes I used for the preparation of all these samples. So here in each column, you have the contents for each sample. So you can play either with the adenosine 4 oligonucleotide, adenosine 8 oligonucleotide, cut aptamer, okay, present in all samples, as I said, adenosine. The stock solution is at 10 millimolar. Don't try to prepare higher concentration of adenosine because you will see it's not soluble at higher levels. And uridine for the control, and then you can add heapest buffer to complete the volume up to 50 microliters in this example. Here are the samples you prepared. Okay, you can find here the legend for all of them. So you can see that they all have the same color because you prepared this sample with similar concentrations. Okay, so something which is very important is the fact that by playing with gold colloidal nanoparticles, you can take advantage of that, because in the case of nanoparticles in the range of 20 nanometer in diameters, which is the case here, we know that if the absorbance at 520 nanomolar is about 1 optical unit, then it means that the concentration of these nanoparticles is about 1.16 nanomolar. Okay, so you can easily quantify the amount of gold nanoparticles by measuring the optical density at 520 nanomolar. Well, after the preparation of all of these samples, you can leave them on the bench for a few minutes. Make sure the temperature is between 15 and 25 degrees and not higher. Otherwise, you will have to cool down somehow the samples. And then centrifuge the samples at 15,000 Gs for 10 minutes. And shake the sample to see what's going on. So you can see here that after centrifugation and shaking, you can get here the typical red color, which is specific to the colloidal gold nanoparticles, on this sample here and on this one here. And indeed, this one is made of both aptamer strands, okay, but in absence of any adenosine. It means that you cannot form the aggregates in this sample. This one is pink, light pink, okay, and this one, the following ones, are almost colorless. Of course, with uridine, as I said, the uridine molecules cannot fit into the pocket made by both aptamer strands, so it means that you cannot form the aggregates. You keep the colloidal gold nanoparticle solution, and then you keep this red color characteristic to the colloidal solution. And here, this is the control, okay? So with the control, the 8 base pairs are long enough to make sure you will form the aggregate, even though there's no adenosine in the sample. So you can see that by forming this series of different concentrations, you can guess more or less what's the minimum concentration that will be used for the detection of adenosine. If you quantify the optical density, so you can do that with specific instruments that will enable the measurement on very small volumes, because don't forget that you have only 50 microliters here in this sample. You can see that thanks to this quantification, I can guess that a minimum concentration of adenosine I can measure with this biosensor is in the range of 0.5 millimolar adenosine. Well, you're done. Hopefully you enjoyed this practical. If you are interested in having more details, you can also have a look on this paper that I published a few years ago in the American Chemical Society Journal of Chemical Education, where I described the principles and experimental details of this practical. If you have more questions, please feel free to send me an email. Thank you to everyone.